Hey everybody, this is Larry. This is May 12th, so it is the 12th day of the May Leetcode Challenge. Hit the like button, hit the subscribe button. Let me know what you think, what you did, what algorithm did you use? Let me know. Let's take a look. A single element in a sorted array. You're given a sorted array consists of only integers where every element appears exactly twice, except for one element which appears exactly once. Find a single element that appears only once. Okay. The solution should run in O of log n time and O of one space. Okay. Oh yeah, because it's sorted away, right? Okay. Yeah, so if it wasn't sorted, then there's that tricky algorithm where you use XOR and stuff like that. And it's a Q algorithm, but it's not. Well, one is it's not relevant here because you want to do it in log n time, and second is that that's trivia. It's kind of annoying actually, to be honest. But okay, let's think about this, right? Well, linear time, this is obvious. Everyone agrees that it's kind of obvious. You just go through the way, and then if like you can figure it out. I'll leave it as an exercise at home to do it in linear time and all of one space even, because obviously you can also put in a hash table and that would work, but that would also just be all of n space and really inefficient. But in the competitive programming, and you wouldn't get this problem per se, but you would just do it if this was given to you in a Leetcode contest, for example. I'll just do an O of n space over n time and then submit it and I'm done, right, in a minute probably. Okay, but now because we want to do in log n time, and obviously you should set yourself to practice the things that you're not necessarily good at. So here, for me, I would focus on doing to solve this in the intended way, even if it's a little trickier. So don't make sure you don't worry about the solution or your how many problems you solve count or whatever. Just make sure you learn, and that's the way that I would try to think about it. The hint here is that you should solve in log n times, right? Well, first thing to notice is that, well, it's a sorted array. So that means that there's some structure to the array that we can take advantage of to solve it in ideally better than linear time, which is log n. And kind of the quote unquote obvious thing with log n is that there are only a handful of log n algorithms. So we're going to start with binary search. And that's probably the way I would think about it. Okay, so binary search is, at its core, a divide and conquer algorithm. That means given something to test, we want to split it in a way such that half the answers are on the, so that every iteration you get half the answers or half the candidates for the answer. So that's what we're going to try to do. And what we would think about doing is, well, trying to find something that is, maybe, monotonically flipping from false to true or true to false, which you can prove is the equivalent and so forth. But something like that, right? So what is true here? Well, for me, the thing to notice, given an array of numbers, if it's sorted, let's just kind of visualize it a little bit with pretty ASCII art. The thing to notice is that, let's say, there's more numbers. Doesn't really matter, right? Is that we look at the middle element. Well, let's just say, for example, do we have to return the index or the element? Okay, it should seem like we have to return the element. Okay, so basically, for each number, I would look to the left and then or to the right. So because, well, first of all, if it's sorted and you look at the left and you look at the right, and you couldn't find a number, for example, you look at 10 and you look at the left, you look at the right, and it's not next to, if the 10 doesn't appear in either of those things, then you're done. Because that means the number is in, well, the number is unique and is the only non-duplicate number, right? But let's say, that's the case, then, well, let's look at the left or the right, right? Well, is there a way to tell, given that these pair of numbers, that the unique number appears on the left side or the right side? Right? Well, if we just do some index subtraction or lookup, right, we'll find that, well, if there's even number of numbers on the right side and, what was it, 12? If there are odd number of elements on the left side, and these are mutually exclusive by how the problem is constrained, then, well, we want to go to the side with the odd number, right? Because, well, I mean, I think that's because odd number means there's one number out, or odd number out, if you will. Though it could be an even number, but you get my point. So that's the strategy we're going to do to use our divide and conquer, and that's how we let's get started on how to figure out how that works. Cool. So I would do something like left to left is equal to 0, right is equal to n, while left is less than right. Again, with binary search, the way that I encourage is to always examine what you're asking for, and then figure it out, how to reconstruct it as a number from as a subproblem of itself, a core part of divide and conquer. So I know that there are a lot of patterns and off, and around like +1 where to put it and off by ones. But the way I think about it is that I try to solve it from scratch every time, so that I ask myself very precise mathematical subproblems, so that I can, so that the index will come very naturally, right? For example, in this case, if we choose 0 and n, that means that the right side is not, it's exclusive, right? Because you can never hit the n element, for example. So these are things that we'll look at. All right, so now let's say mid is equal to, well, for now we're going to write left plus right over 2. And then now, this problem is a little different, right? You just don't, you don't necessarily do a mid. But now we want to, like as we were saying, okay, let's say this is mid, roughly. I don't know if this is particularly true. But so now we have to find out the adjacent number to see if it is, well, if that this number is unique, right? Okay. So if nums of mid is equal to nums of mid minus 1, and of course we have to make sure that mid is greater than 0. If this is the case, then let's check the number of numbers between 0 and mid minus 2, right? Because if this is mid minus 1, we want to count how many numbers there are here, and between these numbers, well, that's just this index plus 1 is the number of numbers, right? Because index 0 has 1 number, index 1 has 2 numbers, and so forth. So equals mid 1 total numbers. And so now we can check if mid minus 1, and you can have some, you could do some premature optimization, but I'm not going to. So if this is odd, as we said, though you could do even, it doesn't really, it's the same thing, right? If this is odd, that means the numbers on the left side are odd. So that means we want our right to be on mid minus 1, which is the 12th, because it's exclusive, right? So let's do that. Right is equal to mid minus 1. Else, then it has to be on the left here. So, that means that your unique number will have to be on the right side. So you have to move your left to mid plus 1, right? Because this is mid plus 1, right? Because left side is inclusive, just to keep that constant. And that's it for this part. Else, if, so now we want to test the other example. Like, let's say this is mid, we have to check the mid plus 1, right? So else, if mid plus 1 is less than n, which means that we're just making sure that it's bound, then n numbers of mid is equal to nums mid plus 1. So similarly, how many numbers are between, so this is n minus mid. Oh no, wait. This is mid plus 1. So this is mid plus 2. So this is n. So this is mid. Oh, sorry, this is n minus 1. So this is mid plus 2, right? So that means we have n minus mid plus minus brands mid plus 2 plus 1. So yeah. So let's check now if, and I would be a little bit careful on the off by ones, but that's roughly how I think about it. And you could obviously go the other way. Maybe the other way is a little easier actually to understand because it's similar. So now let's say we have mid plus 1 is equal mid is equal to mid plus 1. Then we just count mid minus 1, right? So from 0 to mid minus 1, which means there are mid numbers of number in there. So mid mod 2, let's say that is odd. Then we want, again, the right side to be exclusive. So we want the right to be mid. Else, we want the left to be, let's see, we have mid, this is mid plus 1, this is mid plus 2, right? So mid plus 2. Did I do else F1? There we go. Oops. So if neither of those things are the case, then actually this is the unique number. So we can just return num submit, because that means that the number is either there's only one element or it's not equal to either of the adjacent numbers. Okay, and then at the end, let's just return nums of left, because at the end, left will be equal to right. So let's run it real quick just to check, obviously, because we should always be testing. And I guess I moved this out, so I might as well. So it should give us a similar answer. We should test like one number, the end, so forth. Whoops, one-time error. Let's run it again anyway. So it should give us the same one-time error. Oh, n is not defined. Oops. Relatively easy one to fix. Well, and it looks okay. Do I have any other things to check? I guess not. Because I have the beginning, the end. I mean, maybe just slightly bigger version at the end, but I think this should be representative enough that I think if this passed now, I'm going to submit. And I get questions about when you should be confident to submit. Just whenever you feel confident. And sometimes your past will tell you whether you should be more confident or less confident. As you know which kind of problems you get better at and what problems you're just a little bit bad at. For me, it's binary search, so that's why I always think about it. But yeah, so this is the way I broke down the problem, and this is the way that I do binary search. I think the first thing for me, I always have to think about what I'm asking. And I urge that if you're at home and you're studying, and I think there is a very, it's very common for whatever reason that everyone is like, okay, here's a pattern or template for binary search, and these are the cases in which this is the true. So use it on these cases. And I think there's too much memorization. And I don't know about you, but I always have trouble remembering which one is which, and like I get them confused all the time, to be frank. But the way that I did it, and is that the way how I would solve it in a contest or on an interview, which is that I go over what each of these variables mean. And as you can see, like there's no memorization here. And the only thing that I kind of show is that, if I do this and this, that means that the right will be exclusive of the last element. And I show you my logic here. But yeah, that's all I have. Because, I mean, this is binary search, and this is all of log n times as as this kind of divides the space in half every time. So you repeat halving gets to log n time, and obviously all one space because we only use left, right, and I guess and mid as variables. Yeah, that's all I have for this problem. This is binary search. It's something that I actually get wrong a lot, or at least previously. Now I force myself to go through the process that you see here as I did it. Hope that helps. Let me know what you think. Hit the like button, hit the subscribe button. Let me know if this gives you a problem, and maybe leave in a comment why binary search gives you a problem and whether you're pattern matching or you're just actually solving the problem. Cool. That's all I have for this problem. Let me know what you think. Have a good night, and I will see you tomorrow. Bye-bye.